Uh, Hello everyone, I'm Isaac Opolot.
And I'm Otieno Ambrose Okoth.
So we are going to be taking you through transactional approach that is under parallel computation, which is lecture 11. Uh, Before we continue, please subscribe and at least like so that you get the continuous tutorials. So let us dive in and discuss more about transactional approach in parallel computation. The definition: parallel computation typically refers to a set of operations used to perform a logical unit of work. For example, in database systems and parallel file systems. Transaction approach refers to a module of concurrent processing where multiple processes can operate independently but may need to interact and share information with each other. What do I mean by this? So we have transactions being carried out concurrently. Now, concurrently means we have what? One transaction following the other. After one execution, another follows. So it is concurrent, one after the other. So they share the same what? The same resources. No, what resources do I mean? Maybe like the resources from the memory, where they have maybe like one memory where they collect or where they fetch the data from. For example, maybe when you are doing, for example, maybe let's say in database systems where we have transactions like withdraw and deposits, we looking at a memory where everything is read from and what written to. So maybe like when depositing certain amount of money, it goes to the what? It is maybe like read from the database and what? It's also written back to the database. So all those transactions share the same what? The same resources and it comes from the same memory. Let us go ahead and look at the ethics of transaction approach. So we have atomicity, we have we have consistency, we have durability, and so on. Let us start with atomicity. So transactions are treated as individual units of work. If I'm to take you back to chemistry where we had atomic structures, where we used to learn those atoms and the teachers would be like, what is an atom? And people would be like, an atom is what? Maybe like a unit of something. Remember those things. So I might not bring it out the way you want, but I'm just trying to relate what? Atomicity to parallel computation here under transaction approach. So we are saying individual units of work. That means they are brought together. They are like a form of units that perform a certain work. So all operations with a transaction either succeed together or fail together. This helps maintain the system what? Integrity. So these units of work are either what? Are either okay, actually either succeed together. What do I mean by that? They're either performed or executed together. For example, maybe you have T1 and T2, which is maybe withdraw and deposit. They're either executed together or they fail together. In that we don't have one going through and the other one what? Failing. At least all of them should either what? Succeed or fail. For instance, in case of maybe like system failure or crash, there is never that one that go through and what? The others fail. So there will be what? A rollback where it will go back to the current state. And from the current state, the entire transaction will start afresh. So that is simply what we mean by atomicity. The operations within a transaction either succeed together or fail together. One transaction cannot go through and the other fail. They all have to succeed or fail together. Then transaction, let's look at the exit number two, which is a consistency. So transactions bring system from one consistent state to another. The system should remain in a valid state regardless of the success or failure of individual transactions. So what do I mean by that? Let us dive into database system. Let's assume you have gone to the mobile money and you want to deposit maybe a certain amount of money. So you've told the mobile money agent, I want to deposit 30,000. But initially you had what? And not actually you had 20,000 as your balance in your what? SIM card. So that money that is there is consistent. It doesn't what? It doesn't change. So it keeps on it's the state is what? Constant, like it remains in that original state, it doesn't what? Change. In that maybe like if you checked your balance today, it is maybe like let's say 9,000. The other day it is maybe like what? 20,000 and so on. No, it keeps on. It actually stays at the what? Same state. In that when you deposit money, now the system is updated, your balance is updated and it goes to the next figure. Let's assume you deposited 30,000 on top of the 20,000. It now changes from what? From 20 to 50,000, which also stays in that what? Consistent state. It doesn't what? Also change. So the systems should remain in a valid state regardless of the success or failure of individual transactions. Let's assume there's a rollback that maybe occurred due to maybe let's say a system crash or let's say maybe network issues. You went to the mobile money agent and you're like, please deposit for me 20,000 or 30,000 on top of the 20,000 you have as your balance. Then as he or she was depositing the money, there was network issues. The money does not what? Get updated, or your balance does not get what? Updated to the next figure. So it remains in the what? In that original state where it was. If it was 20,000, it will stay in 20,000. That is now why where we look at the failure. If there was a success, it will jump into what? 50,000, which will now be consistent there. So let us look at the third one, which is what? Durability. So durability also here is just in the same line with what? With consistency, because durability looks at once a transaction is committed, its effects should persist even in the face of system failure. This ensures that the system can recover to a consistent state after a crash. So what do I mean by this? Its effects should persist even in the face of system failure. Let's assume you have gone to deposit money and into your bank account. Now transaction P1 has actually occurred. You've transferred money and it maybe let's say it was committed successfully. So that money or that from that maybe like let's say that activity of updating the database to that current or to actually to that current state now should be what? Should remain in that state. It shouldn't again maybe like change. So in case of let's say failure and so on, maybe if in case of a crash, in case of a shutdown and so on, when these systems recover, it should get back to that state where a committed what transaction was what successful. So it shouldn't what maybe like change to go back to its original state before it was brought to the current state it was before the the failures, the crash, and so on. So that's basically what we mean by that. Then concurrency control mechanism. Actually, concurrency control. Now, these mechanisms are in place to manage concurrent what access to shared resources, ensuring that multiple transactions can execute concurrently without leading to what? Data inconsistencies. So concurrency controls are just the mechanisms we use to manage concurrency. Maybe let's say concurrency of executions or of executions of transactions. Let's assume there's continuous concurrency. Maybe let's actually continuous transactions taking place, and the effects come in where we look at maybe like those crashes and so on. Maybe okay, like let's not jump into the main database issues where those effects of concurrence maybe lead to those specific terminologies in transactions where maybe you find that transaction T1 is what? Maybe transaction T1 and transaction T1 are occurring at the same time, and data of transaction 1 is maybe updated in transaction 2. So we're not going to look at that here right now, but we're just looking at the techniques that are used what to control here, where we're looking at maybe like locks, we're looking at deadlocks, we are looking at serialization, where under serialization we look at maybe like conflict conflict serialization. We're looking at maybe we are looking at other terms. Let me just check for you here. So we are looking at the lock protocols. We are looking at serialization, which looks at basically serial schedule. We are looking at serialization schedule. We're looking at conflict serialization and so on. So we're not going to look at that right now because those are now the advanced things under database systems and so on. So I was just bringing the concurrency controls, those mechanisms, or maybe like locking one what transaction as another transaction is what taking place. Now, as these transactions are being executed concurrently, one after the other, you might find that there's what maybe there is a mix up somewhere. So we are trying to what block or lock one what transaction as the other what is committed. This one can also what follow from behind, and there's that what smooth what execution without receiving those what mix ups and so on, maybe updating of one transaction by another and so on. Then let us look at a basic example. So let's consider a simple example of a banking system where two parallel transactions involve updating the balance of an account. Each transaction represents a withdrawal operation and what a deposit operation. So we're having these transactions as withdraw and deposit, where we're having T1 doing what withdraw transaction. So what basically happens during the withdraw? So the start transaction is what is actually comes first. So after that, we go to read current balance. So what we understand by read the current balance? So the read operation now what reads from the database the current balance of what of the user. Let's assume maybe uh, Isaac has gone to the bank and he has inserted his ATM card, and the first thing he checks is maybe what the balance. So the account balance now is what read to Isaac, that you have what shillings 100,000 as your balance. Then now he will perform a withdrawal operation. Maybe let's say he's deducting shillings 20,000 from the bank. So in that process of deducting, a write operation is what updated, which now updates what the balance. That the balance is what 80,000. So that one is written to the database and it's updated actually. which is now what? Committed, that the transaction is done. So if you wanted to check your balance, you now again go through the what? The same process of checking balance, which is now like the read and so on. So that goes to transaction T2. We are looking at deposit transaction. So same thing starts here. You start the transaction and you read the current balance, which is 100,000. So we then perform a deposit what operation, which is what the add operation of shillings 30,000 into the account. Then after that, the write operation now what updates the balance 2 shillings 130,000. Then we commit the transaction. So in simple terms, what do I mean by this? You've gone to the mobile money place and you're saying, deposit for me this. So initially, someone might take his balance. Or you are going to withdraw money. And let's say someone sent you 10,000. And you want to withdraw maybe like 10,000, which is impossible because it will tell you what? Insufficient balance. So now you'll check your account, your mobile money wallet, maybe to check what amount of money are you left with. So if you checked, that process of checking is what you're reading to check to see the balance that you're left with. And then now when you tell the person to withdraw, let's assume now you've told the person withdraw for me what? 9,000. So after withdrawing 9,000, the right operand is now what? Actually takes place, which now updates your balance to maybe a remaining amount where maybe let's assume maybe how much is removed. Is it 500? Maybe 500 is removed and your account balance maybe will also remain as what? 500. So after that, it is what? Committed. The transaction is done. So you can now maybe continue with another what? Person. So let us consider how transactional approach ensures atomicity, consistency, isolation, and durability. So now we are bringing the X. We're relating it to the what? To the example that we looked at previously. So atomicity here. If either T1 or T2 fails at any point, e.g. due to maybe system crash or error or network issues, for example, the entire transaction is rolled back. So what is rolled back? Rolled back implies what? Reversing or taking it back to the what? To the current state where it was at first. Maybe if the transaction found the balance at 10,000 and due to network issues, you fail to withdraw the money and maybe the mobile money agent told you network is poor. But after everything he did, maybe even after you putting the mobile money pin and a rollback occurs. So it goes back to the original state where your money remains the same. The updating has not yet been done. So it remains in that consistent state. So either T1, in case of T1 or T2 failing due to system errors or crash, the entire transaction is rolled back. So it goes back to the current state where it was, and the balance is not updated. So if it was 20,000 and you're withdrawing 10,000, it remains as what? 20,000. It is not maybe like updated to give you back maybe let's say 9,500. It's not done that way. Then atomicity ensures that either both the withdrawal or actually either both the withdrawal and the deposit happen or none of them what does. That explains what we're looking at in the first step. Then consistency. Before and after each transaction, the system remains in a consistent state. In this case, the total balance remains unchanged. If we consider individual effects of T1 and T2. So we see here that the balance has remained as what? 100,000 due to system failure or crash or network issues. It's staying at 100,000. The balance was not updated, so it has remained in its current state. What basic example would I even bring relating maybe like human beings or something?
Maybe I'll bring it of that.
Okay, so let's look at isolation. So even if T1 and T2 are executed concurrently by different processors, the system ensures that the operations within each transaction are isolated. One transaction does not interfere with the other until they are committed. Now, a basic example here I can even use maybe like, let's say, the traffic lights. Hmm? Let's assume there's a runabout and cars coming from different sides. So one part is what being blocked for this other what section of the road, the vehicles in the other section to cross. So just assume if there was no traffic light, what would happen? We're seeing the other ones coming, these ones are also going. There would be what? A mix up somewhere and accidents would happen. It's the same thing that happens here. In case of maybe let's say transaction one and transaction two happening at the same time, there's always that mix up where you find that maybe T1 is being updated in T2, or T2 is being updated in T1, which is not something good. So we are looking at isolation where we bring in maybe like serialization, where we look at maybe like schedule serialization, where maybe all these what there's concurrency, all transactions are what executed concurrently without interfering what each other. Or we are looking at blocking where one transaction first occurs before another transaction occurs, deadlocks, and so on. So this is just that process of what isolating, as I explained with the traffic light and so on. Then durability. Once a transaction is committed, the updated balance persists, even in the face of system failure. If T1 and T2 are committed successfully, the balance will reflect what? The changes even after the system restarts. So a basic example I would say here is let's assume you're typing your document and you saved it. Then all of a sudden, if it's a desktop, power disappears or chucks and it goes off. So when power comes back, you restart the PC. When you open, you find that it is what in that what state where you left it. But let's assume a point where you didn't save anything and power goes off. What happens? Eventually, you lose everything and you start from scratch, which is what the other part of consistency, where it takes you back to the previous state. If you didn't save your work, it goes back to the previous state. If you had saved it, it stays in what? That specific state. So durability also here actually happens in transactions where you find maybe uh, so let us actually time is going. Let's look at the transactional approach in memory. This refers to a model where memory operations such as read and write are treated as transactions. So previously, when I was looking at the X6 and so on, I was actually bringing these things of read, write. So it is now these operations or operands that are used to what? That are used to update, that are used to actually communicate with the memory. Let's assume someone is updating the memory. That is the read operand. When someone is accessing something or fetching something, that is what the the read, because you're reading your balance. So that means it's going to fetch for you the balance from the database. You're writing, you're updating to the database your balance of the transaction and so on. So that is basically the transactional approach memory, where all these transactions, what share the resources in the same or via the same memory. So without wasting time, let me call upon my friend to take you through the other slides. Then where need be, I will still step in
Thank you so much, Product Isaac, for the wonderful presentation. Uh, please don't forget as well to subscribe and then share this with your colleagues so that they can also get this knowledge that we're trying to pass out. My colleague was trying to talk about transactional approach to memory. I would like to start from there before I proceed. Now, transactional memory works by executing, maybe like now if we are to talk in terms of codes, it works by executing code sections as transactions, which are sequences of read or write operations to appear to execute atomically and in isolation from other transactions. Now, that was briefly on what my colleague was trying to bring out. Allow me take you through the hardware techniques. Hardware techniques play a crucial role in achieving efficient parallelism, concurrency, and performance in computer systems. And down there, I'll be presenting to you some of the techniques used in parallel computation as well as transactional approach in relation, of course. The first one is parallel processing units. Now, as we were talking about parallel processing units, you know the term parallel like comes from mathematics, parallel lines. These are things that happen that these are lines that move in a straight line and they don't meet at any point. So, in terms of processing units, we go ahead to say that multi-core processors incorporating multiple processing cores on a single chip allows for multiple execution of tasks. Each core can handle its own set of instructions independently, improving overall systems performance. For example, multi-core processors in desktop computers, server systems, and gaming consoles. Now, when you're doing an activity on your PC, most of the people don't know what exactly happens inside the computer casing, like out something happening inside the casing that we see out here. You see, like let's say maybe you're watching a movie. Now, when you're watching a movie, remember animations are going on. We are seeing subtitles also appearing on the screen. We're having audio also being given out by the same computer that we are using. So now this is the concurrency we are talking about. Like multiple cores are put into use in order to make all this happen at the same time. Like the audio to be playing in relation to, I mean, next to the video, and then also subtitles coming up the other side. So that's what we are talking about under multi-core processors. We have the SIMD and the MIMD architectures. I remember one of the colleagues discussed this in class. I'll just go through them a little bit faster because time is also against us. The SIMD stands for single instruction and then multiple data. Now, this is where a single instruction is directed into to the processors, but then the multiple like the data that is being handled, the instruction is one, but then the instruction is supposed to cater for a lot of data or multiple data. Under the right up here, we are saying SIMD architecture enables the execution of a single instruction on multiple data elements simultaneously. This is particularly useful for parallelizing operations on large arrays of vectors, for example, image and video processing. That aspect that I was trying to bring up about like maybe watching a movie or watching a song, like a video. We see that the audio is also being played, but then the video is also working. So those are that's the single instruction is the movie you're watching. That's the instruction that directed to the processor. But then the multiple data we're talking about the video being displayed and then the audio being played alongside that as well. To continue from that, we have multiple instructions and then multiple data. That is MIMD architectures. Now, MIMD architectures allows multiple processors to execute different instructions on different sets of data concurrently. Now, this flexibility supports diverse parallel processing requirements. For example, now when we talk about maybe distributed computing, we talk about cloud computing. You know, this is where the aspect of multiple instructions come in. Like in cloud computing, let's say maybe we're having a maybe a video we're having maybe like a video chat or something, like multiple people, multiple users and sending in their instructions. Some are using Some are only opening their microphones, some they have videos on. So all that happening at the same time, that's multiple instruction and then multiple data being handled at the same time. Under that, we also have interconnection networks. Now, under interconnection networks, we see that high-speed interconnections occur when dealing with multiple data, of course, and then when dealing with big operating systems. Like, let's say now we are talking in terms of maybe company data like MTN or something. The speed or the interconnection speed has to be maximum, or it has to be maximized, because we need multiple processors and nodes to make these interactions happen. Like, someone is calling, someone is sending messages, so we need multiple processors to handle that. And when you to go to big companies, you find that you go to maybe a room where they have the interconnection side, like maybe where they run their networks from. You will see that they have a lot of systems set up, like system with multiple processors to enable the activities go on. We also have what is known as hardware transactional memory. That's the HTM. Now, transactional memory support. Under that, we are saying some modern processors incorporate hardware support for transactional memory, making it easier to implement and manage transactions in concurrent programming. Now, here, like processors like make use of the hardware. The processors communicate with the hardware components connected to them to enable this fast and then easier transactions to happen. Like we are talking about withdraw and then deposits. Now, with the use of the hardware systems, maybe the system can slow down a bit to enable, maybe if someone is committing onto the same transaction, the system can slow down a bit so that like the update is done and your data is consistent. And then we have instruction pipelining. Under pipeline processing, we are saying pipelining involves breaking down the execution of instructions into stages. Now, each stage can be executed concurrently, allowing for other transaction throughput, but as well, some can also be executed parallelly. Yeah. So modern processors have multiple pipeline stages, whereby like they have a lot of processors that they put into use to make sure that all these transactions happen like in a pipeline system. Like when you talk pipelining something, it's like we are directing, maybe let's say we are trying to transfer data from here to maybe something like Mooney University. Like the pipeline now, in the aspect of pipeline, is like maybe we are using a pipe to direct the data. If maybe let's say the data is now in form of liquid, that's what pipelining means, like combining data together and then transmitting them to their final stage. So under this, we have modern processors that have multiple pipeline stages that help into emphasizing this process to go on. We cannot talk about the hardware techniques and leave the software techniques, of course, used in concurrency and then as well as transactional approach. Now, under software, we are dealing with algorithms, we are dealing with codes, we are dealing with systems. So we have algorithmic parallelism. This involves the designing of algorithms that can be parallelized in fundamental ways, like having parallel algorithms distribute tasks among us, like multiple processing units to achieve parallel execution. This all happens in an algorithm written by maybe someone back then. Someone sits down and then writes down and is like, I want this to go on like this. Now I want, maybe someone has inserted an ATM card in a machine. These are the processes that the person should go through until it's committed. Now those are the algorithms we're talking about, things that happen internally outside the world, of course. Secondly, we have parallel programming models. Here we are saying threads or processes share a common address space, allowing them to communicate through shared variables. We are saying data parallelism, distributing data across multiple processing units and performing parallel operations on a distributed data. I remember back then when we were in class, I think it was Arnold, the group of Arnold, they were talking, and then they were talking about threads and then processes that happen within the computer system. So here we are trying to say that threads or processes share a common address space. Like let's say different threads were broken down from the main one, so they still share the same address space that they were subjected from, or like ejected from, allowing them to communicate through shared variables. And now that's where you bring in the interconnections of the networks, the shared networks and other stuff. We have task parallelism. Here, this bases on the task-based parallelism. Here, like we decompose a program into a task that can be executed independently. Task parallelism is well suited for irregular and dynamic workloads. Now, a program is distributed into tasks, like it's broken down. Let's say maybe you're running a program maybe to translate maybe from English to Uganda, something like that. There would be the task of analyzing that data is divided, and then the task of translating it is also different. So tasks like are broken down, or a program is broken down into tasks so that they can be executed independently. Maybe the audio, like if we're talking the perspective of a video, maybe watching a movie or something, the video is being processed by another sector, and then the audio by another sector. So these are at the end of the day, you see that the video you're watching is coming out with sound, subtitles, and everything, but these tasks are broken down and executed independently. We also have performance profiling and optimization. We have profiling tools that analyze application performance to identify bottlenecks and areas for optimization. And then we also have code optimizations, whereby we modify our codes to improve their performance, like maybe cache usage, the branch predictions, and instruction level parallelism. Under that, we also have the load balancing. Now, load balancing, just in a layman's understanding, tasks are distributed evenly, balancing, like tasks are distributed evenly amongst the processing units that are available to ensure that every resource is utilized, and then that the task is handled by the machine in a parallel system. And then my colleague was talking about something known as rollback. And I know some of you are asking yourself, what is rollback? How is it related to transactional approach? Now, rollback refers to the process of undoing or reverting the effect system or the effects of a system or a transaction that has been partially or fully completed to the previous stage. Now, as I was saying before, like maybe let's say you're trying to withdraw money from your account, and then it's less, it's terminated. You understand that old transaction fails. It's taken back to the previous stage where you get your initial balance that you had before. Or maybe if you're trying to deposit money onto an account that maybe is performing another withdrawal at the same time, one of the two, either the withdrawal or the deposit, can be set back or rolled back. Like one can be committed and then the other will be aborted, as it is shown in this diagram below. And then how it works, of course, in parallel transaction execution, we have we are saying that multiple transactions may execute concurrently across different processing units, such as CPU cores, nodes in distributed systems, or threads in multi-threaded applications. Now, each transaction performs a series of operations that read from or write to shared resources such as memory, data structures, databases, any information source, maybe the cloud. All these transactions operate following the other, and if one encounters an error, then it will be set back or rolled back to the previous state. And then under concurrency, we are saying to ensure data consistency and to prevent conflicts between concurrent transactions, concurrency control mechanisms are used. And these mechanisms may include the locks that my colleague was trying to talk about, the atomic operations. Those are now mechanisms that help in the rollback process. And then to talk about commit and rollback points, as each transaction occurs or as each transaction progresses, it reaches points where it can be committed or aborted. Like as you saw in the diagram I showed you behind here, like there's a point where the transaction is committed. If it's committed, that means that it's successful. But then if it's aborted, that means that it has been rolled back because it has detected maybe a conflict or some little bit of error in the whole running process. Or it might be a code error, it might be hardware error, or something that is stopping the transaction from committing or finishing up. The commit phase. If a transaction completes successfully without encountering conflicts or errors, it enters the commit phase where its changes are committed to the shared memory. The commit phase ensures that the changes made by the transactions are applied atomically and durably, preserving the consistency of the system. My colleague was talking a lot about atomicity, consistency, durability. Now this is all what we are trying to prove, like by this method of the rollback. We have the rollback conditions. Of course, for something to happen, there are conditions or strings attached. Now we are saying if a transaction encounters an error, or maybe a deadlock, or conflicts with other transactions, it may be aborted or rolled back to maintain data integrity. Now, rollback conditions may arise due to conflicts in accessing the shared resources, or violation of integrity constraints, or system failure. Maybe a rollback can even happen maybe during authenticity, like when you're trying to maybe log into your own ATM account, and then you mistake with the pin or something, you can be rolled back like that. All process is terminated. That's what we are trying to talk about as rollback. Now, as some programmers may be running their code, these runtime errors, they can also stop your code from executing what's supposed to do. So rollback is basically a mechanism that is used to avoid conflicts from other conflicts to happen, like in a transaction. Let's say if you're performing a transaction and you don't want maybe to experience an error, you should maybe like check on the system, maybe something like that, something that will eliminate the errors. Maybe if you're trying to withdraw money, you should know that make sure that you have the right amount, your balance in the account, you have your pin with you, something like that, so that you don't get the aborted transactions. To finish up, we have the rollback procedure. Now, upon detecting a rollback condition, the system initiates the rollback procedure for the affected transaction. So if maybe like there's a conflict, maybe wrong pin, before the system sets the transaction into a rollback, it starts by processing or analyzing the affected transaction. It first processes it to see what maybe went wrong, so that you can either be maybe given an error message or aborted like immediately. So here, back to the write-up, we are saying rollback involves undoing the effects of the transaction by reverting any changes made to the shared resources. This might be account balance change, this might be maybe account name change, maybe any change that you make to the shared memory. Those are the things we are talking about. Any change that you make, if a rollback occurs, just know everything will be taken back to where you started from. It's like maybe you're typing something and then power goes off. The last place or the last section where you saved your work, that's where it will go. Now that's how the rollback works. Any error that is experienced, you're taken back to your last point, the last committed point of the transaction. Thank you so much for listening. This has been Ochenambros Okojo and Opolot Isaac. If maybe you have any question, you can drop it in the comment section, and please don't forget to subscribe and share this with your colleagues. Thank you so much, and thank you for listening.